All righty. So E-7, behavior of accumulation functions. I want to say there's nothing new here, but there is some new stuff here, but it's very related to something we've done in the past because you've seen these tables in the past before. So we know that if you have an accumulation function, which is a very specific type of integral, it starts with a constant on the bottom and only has an x as its upper bound or its upper limit. And if I haven't made a typo, the integrand says f of t dt instead of f of x dx. But either way, this is what you're looking for, a number and an x at the top. We know that the derivative of that big F is just little f. I don't want to connect to your headphones. I really don't want to connect to your headphones. Yep. Okay, you're good. This is the world we live in. Let's see. If you wanted to connect those headphones, you would like hit 15 buttons and it still wouldn't connect and you wouldn't know why, but that's how Bluetooth works. Bluetooth knows your intention, and if you actually want to connect, it fights you. So that's just how Bluetooth works. It's part of the same. Since f has a derivative, it is differentiable. I mentioned that yesterday. I know there's like a weird question somewhere where that comes up, so that's why I keep saying it. If you have an accumulation function and this function inside is just your normal continuous function, then f is differentiable, which means that the accumulation function itself is continuous, because if you're differentiable, you're continuous. We're going to look at some other properties of these functions, like all of the properties we look at: extrema, relative extrema, global extremative, concavity, points of inflection, using the same techniques we used in the past. These tables from D6 can be useful. When I gave you these tables, I included the right side back in the previous unit. We just didn't know exactly what all of it meant. But the idea is that we sort of have these relationships between functions, their derivatives, and now we can even think of their antiderivatives. So let's review, starting out over on the left. If you have a function that is concave up or concave down, what's the first thing you think of as far as the derivative? The function that is concave up, what kind of defines that? Jack has two fingers up, so that's second derivative. And if you're concave up, the second derivative is, if you're concave up, no, positive. The second derivative is positive. I know. Yep, that's what I'm gonna work my way back up to that one. So if you're concave up, and probably defining is the wrong word, but the thing we first learned was that meant that the second derivative was positive, and if you're concave down, the second derivative is negative. And again, then that leads us to kind of the next column. If your function is increasing or decreasing, what derivative do we generally think of? The first derivative. And if you're increasing, the first derivative is positive, and the second derivative is negative, correct. So because of that, because the relationship here matches the relationship here, this is a derivative, this is a derivative, we can copy the increasing and decreasing in here. And that's it. The pluses and minuses, that diagonal kind of ends our table. The remaining blocks don't get filled in. But we can also use the fact that those derivative relationships exist between a function, an antiderivative of the function, which is an accumulation function, and its derivative, and also say the same thing. So if I ask you, like, the difference between unit E and what we've done in the past is the function I'm going to be asking about is the accumulation function, and it stands in for what we used to think of as the function. But now the function has moved to the middle row. So if you're working with an accumulation function, you want to look down this column, basically to answer your question. Really, as long as each step down is a derivative, this table holds. That's why we're allowed to have both sides. F of x has a derivative f prime. F prime of x has a derivative of f double prime. The accumulation function has a derivative of f of x, and that has a derivative of f prime. So it's just kind of like where your starting point is. Is your starting point f? Is your starting point the accumulation function? Okay. All right, so let's fill in this second table. This kind of goes right along with what we were looking at in the other table. So if I am at a relative extrema, what do I have at for f prime? 0. If I'm at a point of inflection, there's also something that equals 0, but what is it? That would tell me I'm at a relative extrema. That would be f prime, still f prime. Ooh. It is f double prime, yes. Yeah. We always have this diagonal movement in our table, but this table actually, the diagonal kind of goes the other way. It goes down. Yeah. I got you. Oh, gotcha. Yeah. Yeah. So relative extrema is happen when you have your f prime equals 0. I guess we should be putting equals 0 or undefined. That is definitely an option as well. And in both cases, we need to have a sign change around it. So in each case, we've got to have a sign change that occurs. So it might be a relative extrema if it equals 0. We call that a critical value. It's a critical value no matter what, but if the sign change doesn't happen, you don't have a relative extrema. When we're talking about points of inflection, we've got to have that sign change. We don't have a special word there. We just say possible point of inflection if we know that it's 0 or undefined, but we have to verify it. Okay. So now this one, again, this table kind of works sort of a different way. If I'm at a relative extrema in f prime of x, actually, no, I shouldn't say that. If I have a relative extrema of f prime of x, I want to make sure I answer this. I'm asking the wrong question. My brain just went ahead of me. We've got to fill in another blank in this table, and I've got to figure out which one it is. Is it this one or this one? Can you tell a point of inflection from f prime? Oh, yeah, I know what it is. If, yeah, this table does go the other way. If I've got this situation here, I know I've got a relative extrema. So basically, I can take this and carbon copy it over here. That's what we're going to put. Yep, relative extrema. Because this relationship always holds. So if I have the same thing down here, I can put it up there. That is what I was trying to say, but didn't have fully thought out in my head when I started talking about it. Can we get a relative extrema from f double prime alone? No, and the reason for that is if you know f double prime, there's no way to get back a value from, when you work your way up. If I just know f double prime, I know nothing about the values of f prime. So how do I know if it's 0 or undefined? So this table kind of works in the opposite direction. It's the lower left that's empty, not the lower right that's empty. Okay. So these are a reference. You should go back and look at these as you're working on problems if you're not sure what to look for. All right, so let's do a quick example with an accumulation function. We're going to kind of actually sketch a graph of this accumulation function based on the information that we come up with. So we're going to let f of x be the function x squared minus 2x. And then g of x is the accumulation function from 0 to that x value of that function. So we want to find g prime and g double prime first. So if g is the accumulation function, what's g prime? It's just f, yeah. Just the f. It is f of x. The integrand is the derivative if it's an accumulation function. So g prime of x is x squared minus 2x. And that makes G double prime f prime of x. And since we have that explicitly, what is f prime of x? Yep. All righty. So we want to find the relative extrema and the points of inflection there. So let's go ahead and factor x squared minus 2x. Take the x out, x times x minus 2, which means that my critical values are, I don't want an equal sign there, 0 and 2. With the sign chart, all the regular stuff, we haven't done one in a while, but x is positive before it hits that 0. So, or sorry, it's negative before it hits that 0 and positive after. 2 is negative before it hits the 2 and positive after, giving us our kind of standard sign chart of plus, minus, plus. So we have a relative, we have a relative min at what value? Yep, x equals 2. And relative max at x equals 0. Second derivative for point of inflection, just a linear function. What x makes that 0? 1, right? The sign chart there is really easy as well. That 2x minus 2 is going to be negative before you hit 1 and then positive after, right? If I put something smaller than 1 in, I'm going to be subtracting 2 away from something smaller than 2, which gives us a point of inflection. Find the zeros, or undefined, but this was a polynomial, so find the zeros, verify the sign change, say what you've got. All right, so I want to find the values of G where it reaches the extrema and sketch the graph of G. So I actually want to know what the G of 2 is and the G of 0 is. G of 0 is easy. It is the integral from 0 to 0 of f of t dt, which is just 0. G of 2 is a small amount of work. It is also f of t dt, but I'm going to write x squared minus 2x in this time. Don't forget my dx. And I've got to do some antiderivatives. Antiderivative for x squared is, that would be a derivative of x squared. Yep, x cubed over 3 minus antiderivative for 2x, x squared. Yep, 2x squared over 2, but those 2's cancel. And I've got to evaluate that from 0 to 2. But I really just need to evaluate that at 2. Yep. So we end up with 8/3 minus 4. And of course, minus 0, but yeah, we don't care about that. So we got 8/3 minus 12/3. Sure sounds like negative 4/3. Did I do that right? Yeah. 4, that minus 4 would be negative 12/3. 8 minus 4 is negative 4. Okay, so we know a couple things about our function. We know that the g of 0 is 0. We know that the g of 2 is negative 4/3, which is 1 and 1/3. We know that our function is increasing, decreasing, and then increasing, and has a point of inflection somewhere along the line here at 1. No, 2 is the x value. The g of 2 is negative 4/3, right? So that's the point 2 comma negative 4/3. So we are increasing, and we are actually concave down up until we hit 1. So we're increasing up till 0, concave up until we hit concave. Oh, sorry, I'm going too fast. We are increasing up until 0, concave down up until 1. So we kind of look like a parabola here. At 1, the concavity changes to concave up. We're still decreasing. And our function looks something like that. So increasing from negative infinity to 0, we sure are. We started decreasing between 1 and 2. We started increasing again after 2. Point of inflection somewhere around there. And that's our sketch. Cool. Questions on that? Example 2. One with the graph. All right. This is the main thing that you'll kind of be practicing, at least in the first part of the practice. We have an accumulation function. It is going from some constant a to x. We haven't told you what that a is. As far as finding derivatives, that doesn't matter because that has no effect on what the derivative will be. We first want to find the relative extrema and list the increasing and decreasing intervals. So this is a common thing to ask on an FRQ. So this is where you have to have your idea down. We want to find relative extrema, so we need to be thinking about first derivatives. So we have to list what the first derivative is. So we should write out, they're asking us about g, so we've got to tell them what we know g prime is. What is g prime? If that's an accumulation function. F of x. Yep. F of x. G prime of x is f of x. That is 1 point on the scoring guide every time this question comes up. Did the student write that? Did they say the thing that they were taught? If it's an accumulation function, its derivative is the integrand, the thing being integrated. Okay. For relative extrema, we want to find when that thing is 0. This is the graph of f. Usually on an AP question, it would probably be labeled as such with a word here that said graph of f. So this is the graph of f. We need to know when that thing is 0. When is that thing 0? Yep. Okay. Let's start with the relative extrema. Do we have a sign change at both of those numbers? Yes, because the thing we're looking at, which is f, changes signs. So at 3, it's a relative maximum. And that's because always talk about the thing you're looking at. Because when you're talking about f, we've already told them that we're also talking about g prime. So relative maximum because f changes signs from positive to negative. I didn't, you're right. Yeah, at x equals 3. Thank you. And then obviously we're going to have the opposite of that, a relative min at x equals 6 because, actually I missed 2 things in there, because f changes signs, And then it's the same question asking about increasing and decreasing intervals versus relative mins and maxes. Those your numbers that you're going to write are going to be 3 and 6. Let's assume that this function has solid endpoints here because there aren't arrows. So we won't consider this thing going off to infinity in both directions. When is this function increasing? Disagree. When is, I said this function, when is g Increasing. The question being asked, the function being asked. 0 to 3 and 6 to 7, correct. So then it must be decreasing in the middle, which is 3 to 6. All right. Questions on that? There are times where you may have to look at different things on the graph than what we looked at here. That's where know your function comes into play. We identified that g prime, the derivative that we need to answer their question, is f, which is the graph that we are looking at. So we did the correct things about g prime looking at that graph. Next, we want to find points of inflection. So points of inflection, what derivative are we looking at? Second, yep. So we're looking at g double prime. And what is g double prime? F prime, exactly. Again, the scoring guides say, like, this is one full point. You either have it or you don't. You've identified that this is the thing that you're looking at. And we need g double prime to change signs. Going back to our picture, though, we have a picture of f. Right? Or sorry, we have a picture of, we're really looking at f prime. Sorry, that's what I'm looking for. So we're really looking at f prime. So we are looking for relative extrema. Yep, 4. So the only relative extrema we have here is x equals 4. And our justification talks about f. What happened at f to tell us that we had a relative minimum? Well, we have a picture of f, so we want to talk about f. Yeah, perfect. You hit it on the head. Yeah, f changes from increasing to decreasing. As we change, I'm going to write POI at x equals 4. Because f changes from increasing to decreasing. And now for our intervals of concavity. When is G concave up? Before 4. Is it concave up between 1 and 2? No, yeah, we just won't talk about concavity there. Because G double prime is 0, it's not positive or negative. The antiderivative of a flat line is a diagonal line, and a diagonal line doesn't have concavity. So, yeah. So the concave up will be from 2, or sorry, concave down will be from 2 to 4. They'll usually do a good job of asking for open intervals there, so they'll tell you what parentheses to use. Concave down. And then from 4 to 7, we'll say concave up. Good on that one? All right, letter C. If g of 1 equals 0, what is the absolute minimum and the absolute maximum value of the function? Once you see absolute or just minimum and maximum without the word relative in front of them, that tells you we have either an EVT question, or sometimes we get to shortcut the EVT because we only have one critical value. We're not going to be able to do that in this one because we have two critical values. But if a function like only increases and then changes to decreasing, you can say that that relative max is an absolute max. Otherwise, we need to use the EVT, which means we have to list out all of the values. So we have to figure them all out. So we want the absolute minimum value, absolute minimum maximum of G. I probably should have G there instead of the function. But that obviously is what we were looking for. So we really need to make a table here with our endpoints and our function values, or at our critical values, and we've got to figure out the function value on each of them. So we have 0, we have 3, 6, and 7. And you know what I'm going to do? Although that's where I want to put it, I'm just going to be smart about this and put that table over here. You can see both of them. 0, 3, 6, 7. So endpoints and critical values, that's what the EVT says to do. This table is your justification. There is no sentence to write. And we know that the G of 1 is 0. Yep. So our starting point for our accumulation function is here. So what is the G of 0? Disagree. -2. There were 2 units of area. They were above the line, but we're going backwards from 1, so that is -2. 3 is 3. I agree. And that is because there are 2 units of area here and 1 unit of area there. Pi r squared over 4, yes. So this guy is also a 1. And this is 1/4 of pi r squared, where your r is 2. So it's 1/4 of pi times 4. So this guy is just pi. So it looks like we have to take 1 away from our previous value and then take pi away. So 2 minus pi. So that's taking 1 and the pi away from the previous value in the table. And that's kind of how you do these. You just kind of go from your previous value. At 6, I know I'm at 2 minus pi and add 1. So now I'm at 3 minus pi. Boom. Yep, the absolute minimum is at 0, and the absolute max is at 3. Yep. Cool. Yeah. 3 minus pi is -0. It's just 0 point the digits of pi. So that's definitely not the lowest value we have. 2 minus pi is positive. Or sorry, 2 minus pi would be -1 point something. So yeah, so still not enough. Yeah, cool. All right, so absolute minimum. Always read the question. If you have both numbers, say both. So we'll say absolute minimum of -2 at x equals 0 and absolute maximum of 3 at x equals 3. Sometimes they ask for the x value. Sometimes they ask for the v minimum or the maximum. If you have both, give them both. If they're right in the table, it's going to be marked right. If they're wrong in the table, you're going to not get the points anyway. So you're not gaining or losing anything by writing both of those. All right. Verify. There's nothing to write here, but we're just going to verify this using Desmos. I should have this open over here. And we'll see if all of the things are true. That's the wrong Desmos. Always got about 50 Desmos windows open at a time. I don't have Desmos in there either. I clicked on it before. I'll click on it again. 50 of these open at a time. There we go. There we go. Oh, it opened in Firefox for some reason. That's why I couldn't find it. Okay, so that is our function, correct?
No.
Roughly, is it different? It could be just the, is it the scaling? No, it's 2 by 2, yeah. Yeah, no, that's very different. Man, that stinks. Well, we can't verify it. Tomorrow. I'll fix it for tomorrow. I could, but I don't have time if I want to get through the other two examples, which I want to because we have a lot of people who aren't going to be here tomorrow. So, yeah, so I'll pop that up tomorrow and we'll take a quick look at that. But anyway. All right. I actually made example 3 harder than it needed to be from what I had. So fix that upper limit to match. Oops, sorry, wrong one. Fix your upper limit to match mine right there. So it doesn't need to be an accumulation function to do this. Because we know how to find these derivatives even if they aren't accumulation functions. So if h of x is the integral from 0 to 1/2 of x plus 5 of our function, and we want to find a relative minimum and maximum, we need our h prime. Yep. So what is the h prime of x? It is not. We have to do the chain rule here. So we need the derivative of x over 2 plus 5, 1/2. Oop, I'm out of my. And then we have to do the f of x over 2 plus 5. My 1/2 should be blue too. I'll fix that. I don't like that. So by color, that's what happens when we have a non-accumulation function, a thing that we can't call an accumulation function. You need that argument to go in 2 places. It gets its derivative chain ruled on the outside, and then the argument replaces the t. It's the same thing we do with an accumulation function. It's just that the 1/2 is a 1, and the x over 2 plus 5 is an x. So it's, you think you're doing nothing, but you are following that same rule. Okay. So we're going to follow the same sign chart, but the question is, what x value do I have to plug in to get this guy to actually give me a 0? So what we really have to do is figure out, is that what it's going to do? We want relative maximum. So we want to figure out, when does x over 2 plus 5 give us 3? Because I need to take the f of 3 in order to get that 0. -4, right? So we'll subtract 5. We get x over 2 equals negative. Wait. No, it should be negative. How about -2? Because you've got to subtract 5 from both sides. Yep. Oh, x equals -4. I'm sorry. In my head, I was thinking I had to divide by 2 in the end. That's why I was, yep, got it. You're good. Sorry. I did a goof in my head. I was expecting to get 8 there, and then, but that was, yeah. Ignore me. Yep. X equals -4. Yeah. So yeah, so you've actually got to figure out, because if you think about it, if you plug -4 into x, into h of x, then that means you're going to do 1/2 the f of -4 over 2, -2 plus 5, which will give you the f of 3. So the h of -4 is 1/2 the f of 3. Did I say -3? Sorry, +3, which is going to give you the 0 that you wanted. And since this is just linear and normal, you'll still have that same sign change from positive to negative. Yeah. And you can, again, write all the normal justification that we would there. So that's one way that these problems could change. It's usually just a matter of setting the argument equal to the function value that you need. Another way that could happen is example 4. G of x isn't a pure accumulation function because it's x squared minus an accumulation function. This actually is just asking us to list critical values, so we don't even need to find mins and maxes. Sometimes the sign chart can be a little bit much on these ones, and I realized that was the change that I had made to the previous problem. the sign chart just got too confusing. So they just want to know, can you find the critical values? So that's what we're going to do here. We'll do g prime of x, and we will just use our rules of derivatives. It's two things being added or subtracted, so do them separately. The derivative of x squared is 2x, and then the derivative of that accumulation function is f of x. Just f of x, because it's an accumulation function. And if it's a critical value, then this thing has to equal 0. Which means that 2 times x equals the f of x. No. We need things where 2x equals the f of x. Are there any situations where that happens? X equals 2. And x equals negative 6. Those fit this property. If I double the x value, I get the f of x. You know, those are just kind of problem-solving questions. You guys got to work with what they give you. I could have solved them from this line too. I didn't need to go. I thought this line, just kind of getting them, 2x equals f of x, was just an easier way to see it in this table. But if I double x and then subtract the f of x, I get 0. If I double x and then subtract the f of x, I get 0, going back to the original line there. So just two different ways of looking at it. I found the critical values. You're a critical value if the derivative equals 0. Okay. Questions on that? All right. These ones you just kind of have to play around with and work through and figure out how to do them for yourselves. All right. That is all of the notes.